This is Dr. Anthony Filippi, faculty member in the Department of Geography here at Texas A&M University in College Station, Texas. And the focus of this lecture is on electromagnetic radiation principles. The concepts that will be discussed here really underlie a lot of what remote sensing is about. And so your understanding of these concepts is going to be very important. And much of what we'll be talking about in subsequent lectures later on in this course will be focused on how different types of electromagnetic radiation and different portions of the electromagnetic spectrum interact with different types of Earth's surface materials. So we will be starting out here with an overview of the electromagnetic radiation principles, and then we will later move on to these more detailed energy-matter interactions. The energy that is recorded by remote sensing sensor systems undergoes various types of interactions, and we need to understand what these interactions are and how they operate in order to be able to properly interpret remotely sensed data. So in the scenario where the sun is the source of illumination, and just as an aside, that's not always the case. If we have what is referred to as an active remote sensor, the source of illumination would be the sensor itself. But in a passive remote sensing scenario, the sun is going to be the illumination source, again, which is very common in much of remote sensing. So in that scenario then, the energy is going to be radiated by atomic particles at the source. In this case, it's going to be the sun. It's then going to propagate through the vacuum of space at the speed of light. That energy then is going to interact first with the Earth's atmosphere. It will then, or at least some portion of that electromagnetic radiation is going to be interacting with the Earth's surface. Then some portion of that radiation is going to be interacting with the Earth's atmosphere again on the return trip back up through the atmosphere. And then it's finally going to reach the remote sensor, where within the sensor itself, within that camera, it's going to be that electromagnetic radiation is going to be interacting with various optical systems, emulsions, maybe if we're using film, filters, or electro-optical detectors of some sort. This is an image of the sun that was acquired by the Solar and Heliospheric Observatory, or SOHO, back in 1999. And we will be talking about the various types of electromagnetic radiation that's emitted by the sun very shortly. This is the overall sun target sensor geometry, whereby, again, we have solar, what we call irradiance. That's a important radiometric quantity that we'll define very specifically later on. But it's energy from the sun that is propagating through the vacuum of space, interacting eventually with the Earth's atmosphere, which we see in the diagram here. And that energy is going to take various paths through the atmosphere. Some of that energy will be relatively unattenuated by the atmosphere, making its way down to the Earth's surface to our study area. Some of that will be contributing to diffuse sky irradiance due to various processes within the atmosphere. Some portion of that will make it down to our area of interest. Some portion of that will make its way down to neighboring areas that may not be of interest at a given moment. But anyway, the point, one thing that I'll make of this diagram, one of the points is we'll have information from the energy that is propagating from our target, from our study area of interest, that makes its way back up to our remote sensor. And we'll also have electromagnetic radiation that will be coming from other sources. So the combination of those two data streams, if you will, or inputs of electromagnetic radiation to this quantity, this energy quantity that makes its way up to our remote sensing detector, this quantity called the total radiance at the sensor, or L sub S. We'll define that specifically later on. But anyway, it can come from these various sources. Some of that electromagnetic radiation that makes its way up to the sensor is good and useful information for Earth surface remote sensing. Some of it is not. And so we'll describe in detail these various potential paths that electromagnetic radiation can take through the atmosphere, interacting with the Earth's surface, and how it interacts with the atmosphere on its way back up toward the sensor. So we'll talk about those paths in detail. So very important to this conversation, of course, is the concept of energy. And to define it simply, energy is the ability to do work. In doing work, energy is often going to be transferred from one body to another or from one place to another. There's basically three ways by which energy is transferred. It could be transferred via conduction, by convection, or via radiation. So conduction occurs when one body, it could be a molecule or an atom, for example, is transferring its kinetic energy to another by colliding with it. A classic example here would be if you're heating a pan up on a stove, the pan is getting heated via the process of conduction. Another method of energy transference is convection. And this is where kinetic energy of bodies is transferred from one place to another by actually physically moving those bodies. So a classic example would be convectional heating of air in the atmosphere. So for example, if we have different types of Earth's surface materials, let's say for example, we have black asphalt, we have a grassy field, a forested area, maybe a water body. All of these different types of Earth's surface materials have different reflectivities or albedos involved. And they also have different absorption properties, the amount of radiation that it absorbs. So we know, before we get into these specific radiometric quantities and processes that we'll be discussing soon, we know that a dark asphalt surface is going to heat up more quickly than some of these other types of Earth's surface materials. And that heats the near surface layer of the atmosphere more relative to some of these other types of materials. So the air just above a dark asphalt surface during the afternoon is going to be warmer than it is in, say, a grassy field. And these differing albedos and differing air near surface air temperatures gives rise to these air parcels. Specifically, we're going to have air parcels rising more relative to the ambient surrounding atmosphere over our dark asphalt surface compared to, say, again, some of these natural surface areas. So we have this less dense, lighter parcel of air being moved up through the atmosphere, rising through the atmosphere, and this process was started off due to this process called convection. And then another transfer of energy method is via electromagnetic radiation. And this really is of primary interest in remote sensing, since it is really the only form of energy transfer that can occur in a vacuum. So that is what exists, of course, between the sun and the Earth, as well as outer space in general. So we need to get that radiation from the sun to the Earth in order for that radiation to illuminate the Earth's atmosphere and ultimately the Earth's surface, which is going to provide energy that we can sense with our remote sensing device. In discussing the nature of electromagnetic radiation, a very important concept is the wave model of electromagnetic energy. So in the 1860s, James Clerk Maxwell conceptualized electromagnetic radiation, which, by the way, I denote that very frequently in the slides as EMR. He conceptualized that as electromagnetic waves that travel through the vacuum of space at the speed of light. We denote that with little c, and that's 3 times 10 to the 8th meter per second, or 186,282 miles per second. So the electromagnetic wave consists of two fluctuating fields. One of those fields is the electric field, the other one is the magnetic field. Hence, we use the term electromagnetic. And those two vectors are at right angles to one another, and both of those are perpendicular to the direction of travel. This is a diagram of an electromagnetic wave. And again, as you can see here, we have the electric vector and the magnetic vector that is orthogonal or perpendicular to it. And both of those, again, are perpendicular to the direction of travel. And again, this wave is traveling at the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. So electromagnetic radiation is going to be generated whenever an electrical charge is accelerated. The wavelength of electromagnetic radiation, which we denote with the Greek letter lambda, and we see that there, that is going to depend upon the length of time that the charged particle is accelerated, as well as its frequency. Frequency is denoted with little v there. And it depends on the number of accelerations per second. Wavelength specifically is defined as the mean distance between maximums or minimums, or you can think of that as peaks or troughs, of a roughly periodic pattern, and it's normally going to be measured in units of micrometers or nanometers. That's often the types of units that we use for a lot of electromagnetic radiation, especially if it's in, say the optical portion of the electromagnetic spectrum. We'll talk about the EM spectrum here shortly. In much longer wavelengths, the microwave, radio portion of the spectrum, etc., we may refer to those wavelengths in units of something much longer, like centimeters, for example. Frequency is the number of wavelengths that pass a point per unit time. And a wave that sends one crest by every second, so that's going to be completing one cycle, that's said to have a frequency of 1 cycle per second, or 1 hertz, and we abbreviate that with the symbol Hz. And this is a diagram that illustrates what I'm talking about. Specifically, this is a cross-section of an electromagnetic wave, and it illustrates the inverse relationship that we have between wavelength and frequency. Basically, what this shows is that the longer the wavelength, the lower the frequency that we have, and the shorter the wavelength, the higher the frequency. Also note on this that the amplitude of an EM wave is the height of the wave crest above the undisturbed position that we have in this waveform. And on the bottom diagram here, we see that, so if we have a set location where we have a clock, and also note on this particular diagram, we have successive wave crests that are denoted sequentially 1 through 4. And if we have an observer at the position where the clock is, and that observer records the number of wave crests that pass by in a second, that's going to be our frequency. That's going to be measured in cycles per second, or in units of hertz. And we can discuss the relationship then between wavelength and frequency of electromagnetic radiation in terms of these formula that we see here, where c is the speed of light. And so we see that the speed of light equals wavelength times the frequency. We can rearrange this and solve for wavelength or frequency. In this case, we have frequency equals the speed of light over lambda, which is our wavelength. In general, though, we see that frequency is inversely proportional to the wavelength. So again, this illustrates what we saw in the previous slide. The longer the wavelength, the lower the frequency, and vice versa. So if we use the wave model, it's possible to characterize the energy that is coming from the sun, which represents our initial source of most of the electromagnetic radiation that we're going to be recording with remote sensing devices. Specifically, what we're going to be recording with passive, what we call passive remote sensors. Again, it's basically where the source of illumination of our target, of the Earth's surface, for example, is the sun. The exception to that would be active sensor systems. And we'll be discussing those in a lot more detail later, but examples would be radar systems, LiDAR systems, sonar, etc. Again, where the source of illumination of our target is the sensor system itself. So again, if the energy is coming from the sun, And again, we can think of the sun as what we call a 6,000 Kelvin black body, which is a theoretical construct that radiates energy at the maximum possible rate per unit area at each wavelength for any given temperature. Um, that's a very useful concept in remote sensing. And specifically, the total emitted radiation from a black body, and again, we can think of this as again, a perfectly efficient radiator of energy, again, at each wavelength for any given temperature. The total emitted radiation, and we denote that with capital M here, and the lambda subscript denotes, again, that it is a wavelength-dependent quantity. That total emitted radiation from a black body is proportional to the fourth power of its absolute temperature. And this is what we refer to as the Stefan-Boltzmann law. Okay? We express that with this equation here. So it's m, in this case, the subscript here again is lambda, so it's wavelength dependent. That quantity is equal to sigma t to the fourth power. In this case, sigma is the Stefan-Boltzmann constant, which is 5.6697 times 10 to the negative 8 watts per square meter per Kelvin to the fourth power. Okay. So the amount of energy that we emit by an object, it could be the sun, it could be the earth, some other type of body, it's going to be a function of its temperature. Okay, and this is again, very important concept in remote sensing. So this is a diagram that illustrates part of what I was talking about, and specifically, this illustrates thermonuclear fusion that occurs on the surface of the sun, and that process actually generates a continuous spectrum of electromagnetic radiation. And what that means is that it's generating radiation across the entire electromagnetic spectrum, from very short wavelengths to very long wavelengths. So as we mentioned, the sun approximates what we call a 6,000 Kelvin black body. That's obviously very hot, and due to the very high temperature, it is producing what is predominantly short wavelength radiation, even though, again, we're producing a continuous spectrum of electromagnetic radiation from the sun. It's predominantly short wavelength. The example of shorter wavelength radiation would be the visible portion of the spectrum, where the radiation falls between the 0.4 and 0.7 micrometer wavelength range, and that includes blue, green, red, and other colors of light. And that predominantly short wavelength radiation travels through the vacuum of space at the speed of light. Some of that energy is intercepted by the Earth, where it interacts with the atmosphere and some of the surface materials, for that fraction of electromagnetic radiation that makes its way down to the Earth's surface. The Earth may also reflect some of that energy directly back out to space, but some of that energy may be absorbed, and that short wavelength, predominantly short wavelength energy, may then be re-emitted by the Earth as longer wavelength radiation, which is what we see here in the diagram on the left-hand side, where we see the Earth. So as we mentioned, we can compute the total amount of energy that is exiting a theoretical black body. That's one thing that we can do with the Stefan-Boltzmann law. Something else that we can do using radiation laws is to compute what the dominant wavelength is of the energy that is exiting a body. And we use Wien's displacement law to do that. And we summarize that here with this equation here. So we have lambda sub max, and again, that is our dominant wavelength. And that is going to be equal to K over T. K is a constant that equals 2,898 micrometer Kelvin, and T here is temperature in units of Kelvin. And the sun approximates a 6,000 Kelvin black body, as I mentioned, so we can just plug that into the equation down here in the denominator, and we have the constant K, the value that we inserted in here on the numerator. And so if we take 2,898 micrometer Kelvin divided by 6,000 Kelvin, of course the K's cancel, and so what we get is 0.483 micrometers. Okay, so that is the dominant wavelength of electromagnetic radiation that is coming from the sun. As I mentioned in the prior slide, visible electromagnetic radiation is a shorter wavelength, shorter wavelength type of electromagnetic radiation. So that makes sense, right? Because this is within the visible portion of the spectrum. Specifically, it's in the blue portion of the spectrum, which is between zero point 0.4 and zero point 0.5 micrometers. So as just mentioned, the sun approximates about a 6,000 Kelvin black body, and due to Wien's displacement law, we're able to compute what its dominant wavelength is. So it's about 0.483. And also note, just as an aside here, that the EM energy from the sun takes about 8 minutes to travel from the sun through the vacuum of space to the Earth. And that's about a distance of 93 million miles or 150 million kilometers. Also note that the sun, as I mentioned, can does produce a continuous spectrum of electromagnetic radiation that ranges from very short, extremely high frequency gamma and cosmic waves to very long, low frequency radio waves. And that makes sense, again, that short wavelength is very high frequency and it's very high energy because gamma, as we know, is very high energy electromagnetic radiation. It's what we refer to as ionizing radiation. It can cause damage to cells, living cells, etc. And the much lower energy, longer, low frequency electromagnetic waves like radio waves are non-ionizing and safe to cells. And also remember that the Earth can also be considered a black body, but it's a much cooler black body. It approximates about a 300 Kelvin black body, where the dominant wavelength, as determined via Wien's displacement law, has a dominant wavelength at about 9.7 micrometers. So that's much longer wavelength radiation than what we have for the dominant wavelength of the sun. And that makes sense because, again, as we saw in the prior diagram, that the Earth is incoming the predominantly short wavelength radiation from the sun and then re-radiating out that electromagnetic radiation in the form of longer wavelength radiation, basically thermal radiation in that portion of the spectrum. So this slide has multiple blackbody radiation curves from several different types of objects. One would be the sun, which again approximates about a 6,000 Kelvin blackbody. That's the highest magnitude curve that we see on this graphic. And on this chart, wavelength is on the x-axis in units of micrometer, and the y-axis is the relative radiated energy. And we also have the Earth, again, which is about a 300 Kelvin black body, and that's on the lower portion of this graphic. And we see various types of objects kind of interspersed on this graph. We have a tungsten filament at 3,000 Kelvin black body. A red hot object is at about 800 Kelvin, and so on. So we note in general that as the temperature of the object increases, the dominant wavelength shifts toward the shorter portion, the shorter wavelength portion of the spectrum. That's the main point that you should take away on this particular graphic. And again, on this graphic here, to remind ourselves again, the sun approximates a 6,000 Kelvin black body. Dominant wavelength is in kind of the blue to green portion of the spectrum. It's just shy kind of the green portion. So again, at 0.483 micrometer. And the Earth, again, is approximating 300 Kelvin black body. Dominant wavelength at 9.7 micrometers, so it's much longer wavelength radiation, which we see there, and that's again the dominant wavelength of that radiation that is being emitted by the Earth out into the vacuum of space after it absorbs that energy coming in from the sun. the sun is producing about 41% of its energy in the visible portion of the spectrum. That is a substantial portion of the electromagnetic spectrum um, that is being emitted in, well, what's really a relatively narrow portion of the overall spectrum. And again, blue, green, red light, all of those are examples of different wavelengths of light in the visible portion of the spectrum. The other 59% of the energy is going to be in wavelengths that is shorter than blue light, so shorter than 0.4 micrometers, and it's going to be longer than red light, so greater than 0.7 micrometers. Basically, portions of the EM spectrum outside of the visible. Our eyes, as the term implies, are sensitive to the visible portion of the electromagnetic spectrum. Again, that goes from about 0.4 to 0.7 micrometers. And one of the big utilities, though, of remote sensors, especially modern day ones, is that they can be made sensitive and have been made sensitive not only to the visible portion of the spectrum, but to many other portions of the electromagnetic spectrum. And so those non-visible portions of the spectrum contain unique information about Earth surface and atmospheric materials that is unique compared to what we see in the visible portion of the spectrum. So visible is useful, but so are these non-visible portions of the spectrum. What we'll be talking about in part later on in the course is what parts of the electromagnetic spectrum are most useful to utilize and to sense and to extract information from for various purposes in Earth remote sensing. So now I'm going to discuss another very important concept in remote sensing and just in electromagnetic radiation theory in general, and that is the particle model of electromagnetic radiation. So for about a century prior to 1905, we thought of light as a smooth and continuous sort of wave. That's the wave model that we just discussed. But Albert Einstein came along and he found that when light interacts with electrons, it has a very different sort of character. And specifically, he found that when light interacts with matter, it really behaves as though it is comprised of many little individual bodies that we call photons. And those photons carry particle-like properties such as energy and momentum. So physicists today would answer the question, what is light, as light being a particular kind of matter. Okay, that's very interesting. That follows from the findings of Einstein. So therefore, we sometimes describe electromagnetic radiation in terms of its wave-like properties, but it's also sometimes useful, especially when energy interacts with matter, to describe it in terms of its discrete packets of energy, or its quanta. Note that electrons are very tiny negatively charged particles, as we know, and they move around the positively charged nucleus of an atom. Okay? Atoms of different substances make up varying numbers of electrons, and those are arranged in various ways. And we have this interaction between our positively charged nucleus, negatively charged electron, and that's what keeps the electron in orbit. Now, the orbit is not explicitly fixed, but each electron's motion is going to be restricted to a definite range from the nucleus. And we refer to the allowable orbital paths that electrons can have about an atom as energy classes or levels. We can kind of think of it that way. And in order for an electron to climb up to a higher energy class or a higher energy level, work has to be performed in order for that to happen. Okay. However, unless an amount of energy is available to move the electron up at least one energy level, it's not going to be accepting any work. Okay. So if a sufficient amount of energy is received by the electron, that electron then is going to be able to jump up to a new energy level, and we would, when that happens, we would refer to the atom as being excited or in a state of excitement. Okay. And then once that electron is out in its higher orbit, it possesses what we refer to as potential energy. And you guys are familiar with this if you have um, a book that you pick up off the ground and you raise it some level. It has a higher potential energy than what it did at some lower level. Say, for example, if it's down on the floor. Okay. After about 10 to the negative 8 seconds, okay, the electron then falls back to the atom's lowest empty energy level or orbit, and it's going to give off radiation in that process. Okay. So the wavelength of the radiation that's given off is going to be a function of the amount of work that has been done on the atom. Okay. In other words, the quantum of energy it absorbed to cause the electron to be moved up to the higher orbit. So in this particular diagram, we see the electron starting at its ground state. There's excitation where we have a photon that is being absorbed, and then de-excitation. In general, we see that a photon of EMR is going to be emitted when an electron in an atom or a molecule is going to be dropping from a higher energy state to a lower energy state. And we see that dropping down to a lower energy state in the upper right-hand portion of this diagram in subfigure C there. Right, so it's going to be emitting a photon of light whenever we have that electron going from higher to lower energy state there. And the type of light that's going to be emitted, the wavelength of that radiation, is a function of the changes in the energy levels of our outer, what we refer to as our valence electron. On the bottom part of this chart here on this figure is a process known as the photoelectric effect, which I'll talk more about later, and that occurs when we have some type of matter that is subjected to very high temperature. I'll get back to that in a moment. On this particular diagram, we see the energy of quanta or photons that range again from gamma rays to radio waves in the electromagnetic spectrum. Again, it just shows that the visible portion of the electromagnetic spectrum is quite small compared to the rest of the EM spectrum. Over on the left-hand side, we have different units here. We have energy in units of joules. We have frequency in units of hertz, and we have wavelengths here in different units of length. And you can see in the visible portion of the spectrum again, units of nanometers or micrometers seem very reasonable, but as we go, for example, up on this chart, we have much longer wavelength radiation that we could characterize, say, in units of, like in radio waves or microwaves, in units of millimeters, centimeters, even meters or kilometers even. Okay, so very long wavelength, very low frequency radiation toward the top of this chart, and much shorter wavelengths down at the bottom of this chart. And also note that the energy content, we see this on this chart here, for a very short wavelength radiation is much higher than it is for very long wavelength radiation. So we can kind of think of electron orbits as like rungs in a ladder, okay? Which basically means that if we add energy, it's going to move the electron up the energy ladder, and if we emit energy, it's going to move it down that ladder. The energy, though, on this ladder differs from kind of this an ordinary ladder that you might conceptualize, though, in that the rungs on this energy ladder are not necessarily evenly spaced, and in fact, they're not evenly spaced. So what that means is that the energy that an electron needs to absorb or give up in order to jump from one orbit to the next, it may not be the same as the energy needed for some other step. In addition, an electron does not always use consecutive rungs, right? So what physicists call selection rules is what the electrons use. So in many cases, an electron uses one sequence of rungs as it traverses up the energy ladder, and it might use some other sequence of rungs as it descends that energy ladder. So the energy that is left over when we have our electrically charged electron moving from our excited state to a state of de-excitation, that is going to be emitted by the atom as a packet of EM radiation, okay, as a photon. That particle-like unit of light or radiation we refer to as a photon. Okay? And every time that we have an electron jumping from a higher to a lower energy level, it's going to emit a photon, and that photon is basically going to be moving away from that atom at the speed of light. We should also note that various types of materials have color due to the differences in their energy levels and the selection rules that are used. And there is an example in your book, in the Jensen book, dealing with the energized sodium vapor gas that produces the bright yellow lights that some street lamps use. This is actually an older type of street lamp. There's LED lamps that are starting to be used quite commonly now, but that particular example is focused on the sodium vapor lamp. Anyway, I won't go into detail about this, but it's generally talking about how the sodium vapor is energized with several thousand volts of electricity. So we have that energized vapor, and we basically have electrons then that climb up to a high rung on the energy ladder, return back down the ladder in a certain sequence of rungs. And the net result then is that we have a photon of yellow light with a wavelength, in this case of 0.58 micrometers, that's being emitted. And hence we have yellow light that's being produced. So you can look at that example and the associated figure in a little bit more detail in your book. And this figure shows similar information to what we saw in a prior graphic, but basically it's showing that the sun, again, is producing a continuous spectrum of energy going from very short wavelength, high energy radiation, i.e., say for example, gamma rays, out to very long wavelength radiation, low energy content radio waves. For example. The visible portion of the spectrum, again, is a very narrow portion of the overall EM spectrum. And again, we measure that using units of wavelength, say, for example, nanometers or micrometers, as I discussed previously, or we could use terminology like units of electron volts. All of those units are basically interchangeable. I think that's all I want to say on that. Now we should also note that somehow it is possible for an electron to maybe disappear from its original orbit and then suddenly reappear at its destination orbit without ever having to traverse any of those positions or rungs in between. And if that happens, we refer to that process as a quantum leap or a quantum jump. So if we have an electron that goes from its highest excited state down to the ground state in one leap, it's going to emit just one single photon of energy. Okay? It is possible, however, though, for the electron to leap from its excited orbit to the ground state in a series of jumps. For example, it could go from energy level 4, then to 2, then to 1. All right? So if it takes 2 leaps, for example, to get to the ground state, then each of those 2 jumps will emit photons of somewhat less energy compared to the 1 jump example. Okay? But the energies emitted in those 2 different jumps need to sum up to the total of the single large jump. Okay, so that's how quantum leaps work. So also part of our discussion of the particle model of electromagnetic radiation is the quantum theory of electromagnetic radiation. And this was proposed by Niels Bohr and Max Planck. And they recognize the discrete nature of the exchanges of radiant energy that we have. And so what this theory states is that energy is transferred in discrete packets. We refer to those packets of energy as photons, as we discussed, or quanta. And the relationship between the frequency of radiation expressed by wave theory and the quantum is what we have summarized here in this equation. So in this equation, Q is the energy of a quantum, of a photon that we measure in units of joules. We denote that with J. And H is Planck's constant, which is 6.26 times 10 to the negative 34 joules per second. You guys might remember that quantity from, high school math, chemistry, etc., physics. And V is the frequency of radiation.